So maybe just to start with one idea that maybe adds a bit to the introduction, and thank you, Ferdinand, for introducing us both and Studio Biocene, is that we also run at University College London 2 master's programs in bio-integrated design, and have PhD students, and in fact have a laboratory where we do a lot of the research part. So Studio Biocene is really the practice through which we do the projects, and the research and the teaching is done basically through bio-integrated design at UCL, which is a co-run or 2 co-run masters between biochemical engineering and the Bartlett School of Architecture. Now, when we created this in 2018, it was quite a novel setting because biochemical engineers and architects really don't usually and commonly work together on projects, because they deal with very different industries. The construction industry on the one hand, and the pharmaceutical industry sort of mostly on the other. And we just felt that both Brenda and I were interested in scaling up. We were both interested in bringing biological thinking and processes and integrate them into the design field. And we were really, I think, interested in novelty and a radical change. And that's what sort of brought us both together to create bio-integrated design and subsequently the Studio Biocene.
So yeah, perhaps it's worth beginning with the very, very small, first of all. So this is an image of a kind of consortia of moss proteinema, along with sort of cyanobacteria and other microorganisms. And really what we would say we were interested in Studio Biocene is obviously these are fascinating consortia of organisms, but these are also, I think, the idea of working with nature as a medium rather than an inspiration, as you'd alluded to, Ferdinand. So how do we convert what we know about nature, what we understand about ecology, and begin to bring this into a design language, into a design practice? And how do we begin to propose perhaps radical alternatives to what we already see in our built environment?
So a lot has been said about the anthropogenic legacy of us humans on Earth. But actually, one thing that maybe we have spoken far less about is that when you look at a skyline like this one of London, full speed construction, is the amount of surface area that we have added to the world's surface. And if we think that cities and the built environment will basically double in the next 30 to 40 years, these are the predictions, then we will add a phenomenal amount of new surface area to the world. And we both thought there is potentially something that could be a big change, which is that if we start thinking about our surfaces to be actively involved with the environment and with what growth, then the growth that we have and the environment that we create in our cities would be and could be radically different from what we have currently on this image. Now, the interesting thing is that when we zoom in into our surfaces, actually we discover that there's a lot going on that we don't see with our eye, and that is the creation of biofilms, and there are lots of little species, the microorganisms and other plants that grow with us wanting them or not. In fact, we have, as humans, spend a lot of time washing our buildings off from all this biocolonization, when in fact this is one of the great assets we have. Now, there are aesthetic implications with all this as well. You know, we talk about the aesthetics of impurity, but this might be for another talk. The fact is that we are interested in the notion of viscosity, porosity of materials, and the weathering of buildings. It's of great fascination of what is happening there, the consortia of species that grow there, and how they actually help in regulating the environment.
So yeah, for our first, we're going to take you through some projects. And I think for our first project, we're going to go straight to probably the most anthropogenic site that we have worked on so far. So what you can see here is the ground at a place called Barking Riverside. This is the site of, I think, one of Europe's largest land reclamation programs where sort of affordable housing is being created on sites that were former gasworks, landfill. So there's been a huge amount of remediation to deal with a sort of anthropogenic legacy that we have created. So lots of recalcitrant heavy metals, sort of fuel oils, all kinds of things have been sort of been through this site. This particular plot of land is one of the last to be developed at Barking Riverside, and it's what's called a meanwhile site. And for those of you who may be not so familiar with this term, this is, I guess, a square of land or a piece of land where developers are quite keen to activate the space in some kind of way. But it's being used meanwhile because in a few years' time, this will inevitably become part of the last phase of construction. So the ground is pretty dry. It's pretty barren, apart from, you know, what you can see here. Colonizing as sort of the hardy plant species that are able to deal with this sort of landscape, very clay rich, and also home to, yeah, as I say, a host of kind of interesting compounds that are a legacy of the human activity that's taken place there. Now, one thing that we are interested in within our kind of design work and within our research work is thinking very closely about the role of biotechnology and the role of microorganisms in perhaps restoring environmental balance. Now, we work with a kind of range of people who look at things like sort of genetic engineering and synthetic biology right through to microbial consortia. And one aspect we've been thinking a lot about, and surely you probably have been too, are the kind of suitability for bioremediation of these various types of organisms. So something that works very well in a lab may not have the kind of resilience to be able to work on site. And it may have very specific needs that can be facilitated in a controlled environment. But when you go out to a place like Barking Riverside, you have to be able to relax those constraints. So more and more what we're thinking about is, how do we perhaps apply techniques of directed evolution to community structures, but also, aside from forming our own sort of synthetic ecologies, how we can work with the microbiome of the site and actually augment that to be able to do some of the remediation work that's important. So we have this double goals of, you know, sort of improving soil health at Barking Riverside, but also enhancing biodiversity. This is an incredibly interesting and complex subject to unpack, and we'll show you basically some of the ideas that we've had in regards to forming landscape and activating the site, but really setting a brief for ourselves that we wanted to leave no trace. So the aim was to bring as few materials to site as possible, to make use of some new manufacturing techniques, and to also work with what was there and augment it and improve it and remediate through kind of an intervention, looking at this idea of impact printing of soil.
So we are interested in Studio Biocene also to bring computational processes and digital fabrication, advanced fabrication into the system of biological thinking, and with soil and the impact printing structures that are now being done in quite a few places. What we really aimed at was to create a mix of a material, of a soil composite, that is almost like a retardant for its own degradation and how this becomes gradually dissolved into the earth of the site. So we spent quite some time working on these planters and work with the different types of bullet sizes and compression systems in order to avoid basically that we need any mortar for these walls of these planters. So we then installed them at the site, and you can see here this in the first stage where they were introduced, quite clean still. Then we gradually let them spend the winter outdoors. And what you start gradually seeing is that areas of much higher wind exposure, where there's more desiccation, the anthromes, as we call them, remained much more intact. In other areas where we have more moisture, some of the bullets gradually started sort of decaying and eroding away. And as this is a study, for us, it's really important of how this is merging gradually with the landscape, enriching the soil with the properties of our own planters and bullets.
Yeah. So one of our students had previously had a research project looking at the delivery of plant growth promoting bacteria. Unfortunately, for this iteration, we weren't able to incorporate it into the bullets. It's often this aspiration that you have. It's maybe not necessarily facilitated by sometimes the timelines of a project. So what we decided to do later was to create, very much in keeping with the name. So an anthrome is an anthropogenic biome. So what we were looking at was the role of rhizobia in particular and different mixes of seeds. So looking at the role of nitrogen fixation in relatively nutrient poor soil. And so here, as Marcus said, you begin to see the planters are beginning to almost return back into the earth. But what we have done is we've seeded them with a kind of range of different species. And this really only started at the beginning of the summer. So we're going to be monitoring that and seeing which plant species survive, what kind of biodiversity we're able to accelerate, perhaps in relation to some of the kind of existing stockpiles that are on the site itself. And then looking maybe in later iteration of this project into the impact or the effect on heavy metals and other compounds that are present in the soil of this particular landscape. So as Marcus said, we begin to see this amazing weathering process happen with the bullets. And we often find when we teach students, I'm very interested in sort of the aesthetics of decay. When you get on site and you actually see this happening in front of you, it's actually fascinating to watch. So the amount of moisture that these bullets are able to retain, especially during the winter months, is quite extraordinary. So what you can see here and what we've been able to look at under the microscope is the colonization of the bullets already with mosses and various different sort of cryptogamic species. And you obviously have some of the kind of hardy ruderals on site that are happy to colonize everywhere. And really, the process of weathering is also something to kind of study in and of itself in terms of how the size or the morphology of the bullet, not just the composition, impacts the rate of degradation. And we see different impacts depending on the orientation on the site. So the prevailing wind and the rate of drying or perhaps freezing all plays a role in how quickly these sort of anthromes will degrade. And moving on perhaps to another project, which again looks at the role of robotics and fabrication, but takes a slightly different emphasis. So we're looking here at the circular economy. And one of the aspects that's interesting to us is the idea of how we keep molecules in play, if you like. How do we prolong the lifespan of things that we have created? And here on the top left, you can see us on a visit to a facility run by Tate and Lyle. And they're a sugar manufacturing, a sugar refining company, and one of the last heavy industries left here in London, really operating on the Thames. And they approached us because they're really on a pathway to get towards net zero and to look at all of their waste streams and understand how they might be reappropriated or reintegrated into other manufacturing processes. And one of the waste streams that's a result of sugar refining is what's called precipitated calcium carbonate steps. So they inject in CO2 into their liquor. They're able to precipitate out calcium carbonate, which also pulls out a lot of the organics and aromatic molecules. So that's also what helps, I guess, the flavor profile of sugars. So this calcium carbonate has a very fine particle size. It also has a distinct odor of molasses, which divides people as to whether or not they find that nostalgic and beautiful or whether they find it a bit revolting. Anyway, the brief that we had set ourselves is to try and design with this material and to look at different formulations to enable additive manufacturing and to really only work where possible with bio-based binders to be able to produce something that is printable, that has a certain structural integrity and is compatible with kind of large-scale extrusion.
So we built this for the Waste Age exhibition at the Design Museum. This was actually a very important exhibition here in London 2 years ago, where designers really were questioning the role of design in producing waste and how maybe there was a different way of thinking about materials and the reuse of materials and bring this into a circular economy. So we built a set of layers for what we call these cassettes. There were 4 that we built. And here you can see sort of a bit the robotic extrusion. This is a planar system. But the calibration of the material that was new, this CalX material that we had created, and the layers, the number of layers and the height that we managed to achieve in what we call the lamellas, was quite a novel process. It was not a given. It took us quite a few months to develop this, because we have to think this was extruded horizontally, but then was going to be located in a vertical manner in the exhibition. So we ended up having 2 sets of extrusion systems. So the lower one was the first one. We had to stop, then let the material curate for a certain time to gain sufficient resistance for having then the upper layer on top. And as you can see, the surface is quite undulated. So we did some studies on curtain folds that from the distance you would see really as these sort of this macro geometry. And then you would come closer and realize that there was a patternization that we developed with differential growth. Now, the real interest of this proto-architectural wall was not only to create a material, but also was to build something that could have acoustic properties, thermal properties, and potentially the passive control of humidity in space. And we are actually now with colleagues in the environmental design group developing a testing mechanism for these 3-dimensional walls. So we are really interested in using some of these fabrication techniques in order to manipulate the surfaces that we are creating with our materials. And here you can see an ELM, an engineered living material, and Brenda might say a few more things about this. We were sort of extracting, and Prantar Tamuli, our PhD student, was leading this process of extracting some of the surface areas in order to allow some of the back layers to start emerging in this material.
So yeah, another area that I think we find incredibly exciting, and I think really is starting to be at the frontier of biotechnology, but also how we think and how we might design in future, is this whole remit of engineered living materials or animate materials that are produced from the action of living systems. And in the previous example, as the previous video that Marcus was showing, you see a panel that's created through a biomineralization process. And in this work, what Prantar had been doing was looking at the growth of a filamentous cyanobacteria, previously known as Oscillatoria animalis. It has a rebrand now, but what he was interested in was how this might grow and bind silica particles in this hydrogel matrix. So over time, what Prantar has been looking at is not only just the phenomena of growth through this sort of aggregate-based system and the material properties of how it cures, but really trying to get to the bottom of how we can control or influence how the cyanobacteria grow, how fast they grow, and in what direction they grow, because that will be really interesting in terms of directing form, but also enhancing or augmenting material properties in one direction or another. And what's really fascinating about this organism, it's got some clear preferences for different wavelengths of light, and will respond very differently depending on whether it's grown in red light or blue light or white light. And we've been using this and really studying this to be able to accelerate the biomineralization process. So for those of you who may be sort of less familiar with this, it's looking at this action largely as a byproduct of photosynthesis, where the cyanobacteria grow. They're obviously capturing carbon, and through an enzyme called carbonic anhydrase, they're actually depositing calcium carbonate, again, this our favorite molecule, I think, into the matrix. The cyanobacteria also produce these extra polymeric substances, so this kind of gluey, sugary matrix, which also helps to bind the particles. So it's not really just one action that's happening here. It's sort of a multiple set of things that's taking place. And one of the things that Prantar has been really interested in is looking and trying to measure and understand carbon uptake and how the profile of the material changes through the growth of the cyanobacteria. And here you can see a close-up. In this particular example, what Prantar has been looking at is embedding glass fibers in addition to the silica matrix to look at whether we can change or enhance strength properties. And a kind of fascinating property of this, which Marcus will probably elaborate a little more on, is the fact that light can pass through this material. So this is kind of starting to get into a class or a set of materials that are not kind of like anything that we normally have. In terms of its physical characteristics, it's highly insulating, which is no surprise given the materials that it's sort of made from, but also it holds a lot of air. And the insulating properties can be modified by how rapidly the cyanobacteria grow, which I think is quite an exciting discovery on Prantau's part. And yeah, so what we had been looking at was not only just the kind of the characteristics of it in terms of a physical sense, but also in terms of its aesthetics and what that might offer in terms of design opportunities. In parallel, we've also been working with bacterial pigments and looking at other systems, looking at sort of secondary metabolites produced by various different microorganisms, and just introducing the work of Ella Hetherington, who's also, I guess, largely within the kind of same field of engineered living materials. Here, she's been looking at scaffolds and the sort of directed production of pigment and how we might scale that up using automated systems as well for deposition. So she produces a woven structure using robotic weaving process, then coats it in a nanocellulose material derived from bamboo, and then seeds these panels with various bacteria, so Xanthobacterium that produces violacin, or in the case of the right-hand panels, a set of Bacillus thuringiensis that produce melanin. And she's interested in their antimicrobial and semiconductor properties, but obviously just the fact these molecules possess certain properties is not really enough in itself. How do we create form? How do we actually create materials that have or embody some of the properties of these microbial systems? And what we are more and more keen to do is to demonstrate our work and put it into the public domain, but also understand how it responds to the environment in which it's placed. So this is up in Scotland now. So we've gone to the St Andrews Botanic Garden, which is a really remarkable place, which we really strongly encourage you to visit if you ever find yourself up in Fife, where Harry Watkins, who's the director of the garden, has been taking this on a massive journey of transformation. So really trying to unpick what is the role of a botanic garden in future in light of rapid climate change. How do we understand the resilience of plant communities? How do we actually think and study plants and work with living systems to confront some of the challenges that we're going to face? So rather than the Botanic Garden as a museum, it's an active space of research once again. So we've installed the panels, the ELM, cyanobacterial ELM panels at the front, and then the melanin panels on the sides of what we call the bioscope, which is a sort of pavilion that's been constructed to house this living laboratory. And here you can see us on a rather gloomy day in the winter after we've finished installing. So I think one of the most joyous aspects of working in this field, I'm surely you find this too on the ECOLOPES project, is the interdisciplinary interactions and the necessity for sort of this teamwork, but also exchange that really underpins the kind of radical solutions that we really need to think through and develop together as designers, as scientists, as engineers, rather than this idea of the lone inventor, which I think is terribly outmoded. So this is really, I guess, a picture of us. We look kind of tired and serious, but we were very, very proud of what we've been able to make at St Andrews.
So Brenda mentioned the bioscope. So this is what we call this. And initially the thought, and this is where things become interesting and complex. Initially, we thought to clad this little pavilion with these biological materials, but we knew that we couldn't just expose them to the harsh Scottish weather without testing it sufficiently. So what we did is we cladded the interior. So we basically inverted the idea. We got to a point where we realized the structure was going to hold up the panels, had to go outside and gain depth in order to control somehow the amount of exposure to rainfall and to the to the entire climate around. And then at some point we started drawing and designing it, and realized that actually this is a little pavilion, a little folly in the park that becomes actually a really important attraction point where people sort of walk around and realize, in the old English garden tradition, that the little folly gives you a completely new orientation in the park. And so we designed this, and bear in mind there's a tree behind, over the tree roots. Now that was in itself a very complex issue because this obviously doesn't have any foundations. It's basically sort of floating over the ground in order not to affect the roots of this oak tree behind. So the notion of the expressive quality of architecture and how this creates a level of empathy. In fact, some people then called it the Scottish thistle because it does have a sort of spiky quality. It's all part of a strategy that makes people embrace and create curiosity and go there and feel that they're part of something. Now, in Studio Biocene, we're very interested in scaling up, as I said at the beginning. And one of the things we have been looking at is the importance of typologies in architecture and how maybe with new concepts of the microbiome, of how the whole climate change condition is actually forcing us to think of how we live and what our spaces are going to be, how they're going to be organized. And the idea of the microbiome really brought in this possibility that we create these infolds in the house and bring the outer in. And on the top left-hand side, you might just see these little diagrams. And this is just a very simplified sequence of key typologies throughout the centuries. You know, the courtyard house towards the sequence of adjacent rooms, then the introduction of the corridor, then the plan libre. And then you get sort of to the house of the future of Allison and Peter Smithson with this sort of distribution of different cubicles that start organizing the house, so there's no wall anymore. And then the idea of the Biocene house 1.0 is sort of to introduce an organization that is done through nature rather than the prototypical sort of walls or partitions that we usually used. And each of these infolds has different roles to play, from bringing sort of nature in through the entrance, but by having also water and a collection of water from the roof. And we did this as part of a competition project for the London Festival of Architecture of an eco house that we were shortlisted for. They unfortunately didn't have then the money anyway to build this, but we were involved with Price and Myers, the engineers, to think about a very sustainable construction of such a house. So here you can see sort of the image of the roof as the grand water collector, but in urban environments, the water is not pure. So there needs to be some bioremediation that happens on some of these points, which we call the vertical gargoyles. And that is the collection points where the water comes down is then reused for the house. We are very interested in bioreceptivity, and one of the walls of the house was going to be cladded with these bioreceptive panels. And we are interested in what we call the poikilohydric living walls. And that is to create porous material matrices with geometries that allow cryptogams and the cryptogamic surface cover to expand in time. So accelerating basically the weathering process on walls. And this is a case in Edinburgh, in Scotland, again, where we have installed these panels on a housing extension and where we're monitoring this throughout time.
And funnily enough, in parallel, this is yet another wall, but of a slightly different nature. So a lot of the research that I've been involved in looks at the role of microalgae and in particular immobilization as a way of activating biological systems for applications, environmental applications. In this particular example, we were interested in a case study looking at cadmium, and this wall was produced and led by a PhD student, a first doctoral student of ours, Shanil Malik, who was looking at this case study of small-scale artisans in India and thinking about how wastewater treatment in particular could be decentralized, but also thinking about the aesthetics of that. And rather than making this something which is buried, which is hidden away somewhere else where waste is carried away, how we can actually be proud or have an identity that relates to our relationship with water and how form and geometry can also influence residence time and enhance bioremediation. So this project has many layers in terms of its ambitions and what it sought to do. And I think a beautiful element of this was this relationship with water and the dripping and the intimacy of water. We've read aesthetic water is this kind of element that is very fundamental to us. Sensuality, it has a sound, it has a dynamic. People were captivated by this wall, the way it looked, and then were more intrigued when they were able to find out what it did. And for me, as a biochemical engineer, normally in my discipline, we design kind of fundamentally quite ugly things that normally people don't see, or they admire it for its technical capability rather than its aesthetic qualities. And it's really been quite a revelation to me to work with form and geometry and this idea of the very public demonstrator as a way of communicating and interrogating the way that we do things. But it's also been quite an interesting dimension because people see it as artistic and they can't necessarily reconcile that these things have multiple functionalities.
In fact, one of the key ideas of this project at the time was to design these tiles for India. And we looked at the cultural legacy of some of the Indian most important patterns. And the peacock patterns in the Royal Palace of Jaipur came to mind. And there was a sort of sense that if people understand that this is not a bioremediation machine, but it is actually a piece of ornamentation that has a cultural sort of embedded quality, then there's a totally different way how people will embrace this novel technology and how they will want to place it in industries and different walls and see this as something to do with their own heritage. So we are interested in this bridge between cultural aspects, the technology, the performance of the materials, and how this creates sort of novelty altogether in terms of its language.
And like many of you, I imagine as well, we sort of went into the pandemic having done something like this and then having a lot of time to really think about it. We were writing an article for a publication which has just come out from Brill, a book called Being Algae. And one of the, I guess, limitations, if you like, of the Indus project was this process of immobilizing the algae in the hydrogel and applying it to the tiles. Now, the idea of the algae bound in a matrix that would hold or retain water was very, very important. And the idea of water flow, indeed, over a surface. So we sort of set ourselves the challenge of how we might reinvent this with the idea of creating maybe stable consortia of organisms. And again, as Marcus mentioned, we think a lot about the aesthetics of the biocene, so of patchiness, of heterogeneity, how we might become more familiar with this and how we might actually adopt it or accept it in close proximity to ourselves. So to that end, we had devised or designed or been invited, in fact, by Jane Withers, the curator of the water pressure exhibition in Hamburg. So it's still on at the MKNG until October, I believe. So we've installed what we call augmented polycultures. So this is a structure which has been 3D printed from ceramic with the goal of hosting or becoming inhabited by these amazing kind of consortia of algal biofilms. And over time, the idea was that we would inoculate it and then watch it grow and change over the course of the exhibition.
So we did lots of studies in terms of its surface quality, augmenting. In fact, we realized that in Studio Biocene, in BioID, we spend a lot of time thinking of how to maximize surfaces, how to create more of an area where we can have exchanges with the surrounding climate, where we have more water running over. And here we were looking at the textural qualities, the three-dimensionality, this porosity. And in fact, this is closer to a grotto than anything else. It's almost like a two-dimensional grotto. We did studies with water flows. We looked at how long the residence time was going to be from the top to the bottom. We did smaller prototypes and then bigger ones. And we spend a lot of time after doing these non-planar ceramic extrusions, thinking of how we were going to assemble all this, thinking that this was the vertical gargoyle for the Biocene house. So this, you have to think, is sort of part of a little, it's a little sample that was going to be integrated into a much bigger project later on. So this non-planarity was actually really quite challenging, so that it can adjust to different heights and different positions. And as Brenda was saying, once installed in Hamburg, the lab really is the museum. This is where the testing actually of the algae growth is actually happening throughout these months where it's installed there.
Yeah, so this sort of amazing slime, if you like, is starting to colonize the structure. And through a kind of longer research project that's running in parallel to this, we're interested in studying the role of geometry, both in terms of guiding water flow, but also influencing light, and really trying to understand where the algae might prefer to live, but also then how patterns can be informed through geometric explorations to make the surface readable. And again, that's something we've been thinking a lot about in the past couple of years, is the various stages of a design, a biointegrated design over time, because that is, I think, what differentiates us maybe from kind of other products or other perhaps things that you would see quite frequently, maybe be called biodesign, which tend to present either an endpoint or a kind of static element or an inert something or other, more or less, that's been formed into a biomaterial. I think what excites us most and what we really enjoy working with most is this idea of change, this idea of the temporal, and that it brings a different dimension to projects, that you can encounter them over and over again. And you see this vivacity, but you also see the impact of climate and seasonality on the design.
As we have called it in one of the articles, this is part of our attempt to design for aging buildings. The idea that the buildings will not stay the same. In fact, it's a fallacy to think that we as designers design buildings for the first day when the building was launched. No, it's actually years later that the building becomes really alive. And how do we choreograph and prepare the buildings for this type of evolution? We have just to finish, maybe here a list of a few articles that we wrote that might be quite relevant for those who are interested in looking a bit more into some of these topics. There's also more information on the Studio Biocene website, but also on the MArch and the MSc Biointegrated Design. And perhaps just to finish, we have a little film which we still enjoy showing, which was done by a few students of ours here in BioID, which shows a bit sort of the visionary dimension of some of the work when not necessarily physically made, but mostly when it's animated. Thank you so much
Thank
for
you.
listening.
Follow us in this shift to multi-species design through ECOLOPES. Find out more about our research on www.ecolopes.org and on our social media platforms.